Hi, this is Chuck, and I want to welcome you to this video on methods of undetermined coefficients. This particular method is an interesting method. It's fairly straightforward to use, and in the situations where it works, it makes life pretty easy for the most part. Well, what are these situations where it works? First, it needs to be a linear differential equation with constant coefficients. Now, we're going to basically assume that you're going to get this in some form where you have n to the nth derivative plus I don't know, something or other to the n minus 1th derivative, dot, 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 equals, and then you have some kind of a function over here on the right-hand side. So we're talking about situations that are not homogeneous, unlike characteristic equations and some of the other techniques we've looked at that require homogeneous equations. And what's going to wind up happening is we're going to first look at, okay, is this a linear differential equation? Secondly, are the coefficients on the various y terms constants? If those are in good order, the next thing we want to check is on the right-hand side, or movable to the right-hand side, is the function a polynomial, e to the rt, where r is not 1 or 2, so it'd be like e to the 3r, or 3t, or e to the 5t, or something like that. We can also get into complex solutions with e to the I omega t or e to the negative I omega t. And we can also include trig functions like sine and cosine. So these are the four basic types of functions we're going to be looking for occurring on the right-hand side of our function. And by a polynomial, that means it can be to any degree. Hopefully it's not bigger than a quadratic because things start to get entertaining. Now there's another option for the right-hand side, and that is the right-hand side can be a product of some of the four that we just talked about. So for example, we could have a situation where the right-hand side is something like t squared plus 6t minus 2 times e to the 4t. And that's a product, as you can see, of two of the basic types of functions that we just talked about. We'll talk about how do you deal with that when you have a product. It gets a little messy, but basically it's just chasing down um, values for different unknown coefficients. It's not like it's a horrible process. It just takes a little longer. Okay, so the idea here is we're going to propose a solution, and the notation for that proposed solution is y sub p. And the proposed solution is going to be based on what the right-hand side function looks like. And then we're going to solve for the coefficients in the proposed solution. Okay. We'll look at the various functions that are appropriate based on the right-hand side. So based on whether we have a polynomial, e to the rt, e to the I omega t, sine, cosine, some product of those, we'll look at what a reasonable solution is to propose in these different situations. Let's start off with looking at a fairly straightforward differential equation. It's linear, it's second order. It does have constant coefficients. Notice that the y prime, and y all have a coefficient of 1. And then on the right-hand side, I've just denoted some general function f of t. What we're going to do here is we're going to look at several different possibilities for f of t, and then look at reasonable proposed solutions for each of the right-hand side. In the first case, let's take a look at e to the rt. Okay, it's one of those four that we proposed up above. And we're going to propose a solution to the equation y double prime plus y prime plus y equals e to the rt. Notice here I've not defined r other than as we talked about earlier where r cannot equal 1 or 2. We get into issues with resonance there. The proposed solution is going to be y sub p equals k e to the rt. R is going to be some fixed constant in our specific problem. K is going to be an unknown. So for example, we could have e to the 5t. In that case, r would be 5. Our proposed solution would have k as a constant. And then what we would need to do is to compute what this coefficient is. Okay, so when we propose our solution of k e to the rt, it then allows us to compute the derivative. Okay, it's just going to be k r e to the rt. And the second derivative is going to be k r squared e to the rt. This gives us then a value for y, y prime, and y double prime. What we're going to do is we're going to substitute these into our equation that we're trying to solve. So the second derivative will go there, the first derivative will go there, and the y value will go there. And when we do those substitutions, we're going to end up with an equation like what you see here. Now, at this point, notice that each of the terms on the right-hand side, whoopsie-doo-dah, I forgot the k here. Each of the terms on the right-hand side is going to have a factor of k e to the rt. We can factor that out of each of those three terms, and what that's going to give us then is k e to the rt times this r squared plus r plus 1 equals e to the rt. We know that e to the rt cannot equal 0. So we can divide by e to the rt, which gives us then k times the r squared plus r plus 1 equals 1. And we can then also divide by the r squared plus r plus 1. We know that that's not going to equal to 0 because r is going to have to be something like 5 or 6 or something like that. This gives us then a value that we can use to compute what k is. And remember, k is the constant in front of our proposed solution. Remember, our proposed solution is y sub p equals k e to the rt. We are going to take a look at some scenarios where we define a specific value for r so that we aren't just working in a general solution all the time. But this k value gives us our constant coefficient right there. Okay, let's take a look at an example of how this would work. What I'm going to do is I'm going to start with my equation y double prime plus y prime plus y equals f of t. Okay, so here is that equation. And on the right-hand side, I have e to the 5t. My proposed solution is going to be k times e to the 5t. We've already computed what y or what k is going to equal. It's going to be 1 over r squared plus r plus 1. Well, we know that our r value in this case is 5, so we can substitute in our value of r, 5, and it allows us to then right off compute the value for k. This gives us then a proposed solution of 1/31 e to the 5t. Now, that may seem a little odd, and you may be thinking, well, that was awful easy. Let's check to see if this really works. First, I have my proposed solution. I'm going to compute the derivative of it, which is going to be 5 over 31 e to the 5t. The derivative of the second derivative of the proposed solution is going to be 5 times 5, or 31. I'm sorry, 25 over 31 e to the 5t. Substitute this back into our original equation. Here's y double prime. Here's y prime. Here's y. And when you add those three terms on the left-hand side, sure enough, they add up to give you a coefficient of 1, which gives us e to the 5t, and it works. It's just that easy. Wow. Can life get any easier? Now, one of the things I want to caution you about, and this is important, it's at the bottom of the screen right now. The formula for k varies based on the constant coefficients of your y double prime, your y prime, and your y. Really important, k is not always going to be 1 over r squared plus r plus 1. Okay, let that soak in. That's not always going to be the case. It was the case in the situation that we were just working with, where we had y double prime plus y prime plus y, all with coefficients of 1. Okay, well, what happens if the coefficients are something other than 1? In this particular situation, you can see that we have y double prime plus 5y prime plus 6y equals e to the 7t. Once again, we're going to propose a solution, k e to the, in this case, 7t, which is going to give us our first derivative of 7 e to the 7t, and our second derivative is going to be the 49k e to the 7t. We can take these, substitute these into our original equation. Now, the thing to be careful of is when you substitute in for y prime, there is a coefficient of 5. And when you substitute in for y, there is a coefficient of 6. This is going to change our computation of what the formula for k is going to look like. When we substitute in the y prime, and a y double prime, we're going to get 49k e to the 7t plus the 5, which is the coefficient from y prime, times the derivative of our proposed solution, plus 6, the coefficient of y, times our proposed solution equals e to the 7t. As with the previous problem, there are a couple of factors common to each of our terms. Those are k e to the 7t. Notice that leaves us then with a 49 on the first term, 5 times 7 is 35 on the second term, and 6 on the third term. These are going to be added up and then multiplied by the k e to the 7t, and it'll give us, when we add these and when we divide by e to the 7t, which is perfectly fine because e to the 7t is never 0, this is going to give us k times 90 equals 1. It gives us the value for our constant in this particular application is 1 over 90. We can then use that to adjust our proposed solution to be y equals 1 over 90 e to the 7t. We already in an earlier problem, the one up above, demonstrated, okay, there we go. Once we got our proposed solution, we took its derivative and then we computed the second derivative, substituted those into our function, and verified that it worked. I'm going to leave it for you to go ahead and verify that our proposed solution here, 1 over 90 e to the 7t, truly does work as a solution for this equation. All right, a second function on the right-hand side that we talked about is polynomials. If you have a polynomial which you want to propose as your solution is going to be a polynomial where you have the same degree as the original function we're looking at. So that's a first degree, so we needed t to the first power. I'm going to need to incorporate some coefficient there. Now you also have to be careful because even though our polynomial on the right-hand side is just t, we need to account for all of the powers of t less than t to the first. So in this case, that means we need to also include a constant. If this was f of t equals t cubed, our proposed solution would be at cubed plus bt squared plus ct plus d. You need to include all the powers of t less than whatever the degree of that polynomial is. Okay, so here's our proposed solution. The derivative of our proposed solution is going to be a, and the second derivative is going to be 0. We can take these values, y double prime, y prime, and y, substitute them into our equation. Now remember, y double prime is 0, y prime is a, and y is going to be a times t. Well, a times t, it just doesn't want to write in that area. That's interesting. Anyway, our y value is going to be this a times t plus b. When we substitute these in, still keeping the t on the right-hand side, Goodness gracious, this thing's going crazy on me. When we substitute these in, we're going to wind up with this equation that we have here on the right. That's going to be a plus a times t plus b equals t. So just like solving a system of linear equations, we're going to create an equation that just has the same power of t. So we have a times t equals t. That means a equals 1. We're also going to we have these constants a and b, which is going to give us a plus b equals 0. Using a equals 1 from our previous equation, this gives us b equals -1. Using those values for a and b in our proposed solution up here is going to give us our proposed solution is going to be a, which is 1 times t, plus b, which is a -1, or our proposed solution is t minus 1. All right, so that's got that. I'm going to leave it for you to check this as well. I don't want this video to get overly long. I'm kind of concerned about it seeming to act up here a little bit with the pen. Let's see if I can get this to accept y of p now. There we go. All right, so we've now taken a look at two possible right-hand results or equations. A third function that can occur on the right-hand side is either sine or cosine. Now, when you compute or start a proposed solution for this, you're going to want to include both sine and cosine in your proposed solution. Notice they're each times a different coefficient. You want to include both sine and cosine because we're not only including the function, but its derivative. And remember, if you start out with sine, you're going to get cosine, and the second derivative is going to take you back to negative sine. But you want to have a solution that provides the option of not only the trig function that's on the right-hand side, but the derivative of that trig function that's on the right-hand side. All right, so we have here our proposed solution, c1 cosine t plus c2 sine t. This is then going to give us our derivative, and I'll leave it for you to compute that. You know that the derivative of cosine is a negative sine, and the derivative of sine is cosine. Well, I guess I just did it for you. Okay. And then the second derivative comes by computing the first derivative. As we've done in earlier problems, what we're now going to do is we're going to take our y, y prime, and y double prime and substitute them into our equation, y double prime plus y equals sine of t. Okay, so here is our y double prime. Here is our y prime. And you can see here is our y. And then the right-hand side kind of ran out of space, so it's down there. But I want you to realize that we have every term from the original equation accounted for in our substitutions. At this point, it's a matter of going through here and seeing what will cancel. For example, we have a negative c1 cosine here, and we have a positive c1 cosine there. Those will cancel. We have a negative c2 sine. That'll cancel with c2 sine. And that leaves us then with this negative c1 sine plus c2 cosine equals, and our right-hand side continues to be sine of t. Notice in this situation, what's going to wind up happening here is our sine of t on the right-hand side will correspond to this negative c1 sine t on the left side. If we divide both sides by the sine of t, obviously we're going to have to limit our domain here so that we can avoid dividing by 0. But what we wind up with is negative c1 equals 1. The right-hand side is going to be 1 when you divide by sine. If we have negative c1 equals 1, that gives us our solution that c1 is -1. The second term on the left side is cosine. Realize that there is actually a cosine term on the right-hand side. It's just cosine of t, but it's multiplied by 0. Oh, that gives us that C2 is 0. We don't see it on the right-hand side because when you multiply by 0, it's just 0, so we leave it alone. All right, this then gives us the values. It allows us to determine the values for the coefficients on our proposed solution. C1 is going to be a -1. C2 is going to be 0. And it allows us to then report a solution of negative cosine of t. You can check this to verify it. All you need to do is to compute the derivative, compute the second derivative, and substitute those back into the original equation in the upper left corner here. And the right-hand side, which is sine of t, should wind up equaling the left-hand side, after the left-hand side is simplified, also sine of t. Okay, now one of the things I mentioned here, and I already talked about, is that, whether you start with sine or cosine, the proposed solution is going to involve both sine and cosine to allow for the derivative and other odds and ends that can come into play. Let's take a look at a fourth possibility for the right-hand side. This is going to be where you have an exponential function, I omega t. Uh-oh, we're talking complex answers now. Yeah. Okay, so what's going to happen here is we're going to continue working with the same left-hand side. The right-hand side now is going to have a different function. How do we go about managing this? Well, the way we're going to compute a solution here is we're going to propose our solution y of p equals m cosine plus n sine. Okay, as we work through this, you're going to see that the derivatives are going to be a little messy with this one. Okay, but it's okay. It's just a little more messy. It's just more algebra. It's not like it becomes more difficult. It's just more of the same stuff. Now, you may be thinking, that's kind of odd. Where do you get cosine of omega t, sine of omega t, when we started out with e to the I omega t? Where'd that come from anywhere? Anyway, well, it came from using the Taylor series expansion of e to the x, okay, courtesy Euler himself. What I'm going to do is I'm going to let beta equal to the omega t to kind of clean things up a little bit. And if you evaluate e to the beta I, you're going to wind up with 1 is the first term. Now remember, the exponent is the second term, so that's just going to be beta I. This next term is going to be beta I squared, which is going to be beta squared. I squared is a -1, so it's going to come out as a negative. When we substitute beta I into our third term, I squared is going to give us a negative, and then we're still going to have an I, so this is going to be b cubed with a negative and an I. And you can continue with each term substituting in bi to the appropriate power and figure things out. Now, notice here that there are some terms that have a complex or imaginary element to them, and there's some that do not. The terms that do not are all even powered, and in fact, it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, which you might recognize as being the cosine. Really? So what winds up happening is we can take the expansion, break it into two pieces. The first part's going to be cosine, and then if you take all the odd powers, remember sine is an odd function, an odd powered function, take all those and ta-da, you have sine. So this is where we come up with, why do we wind up doing the cosine and the sine? Well, there you have the reason why. As far as actually working a problem with this, it's the same as with the other things. I'm going to work some problems in a second video. I was just concerned about this video getting too long. So in this video, we're going to present the ideas, and then in a second video, I'll provide solutions or problems with solutions. All right, there is a fifth possible right-hand side function that you can get with this non-homogeneous linear constant coefficient equation. That is any of options 1 through 4, if any of functions 1 through 4 can be multiplied together. So for example, suppose our function looks like t e to the rt. Once again, we're assuming r is not 1 or 2. In order to get a proposed solution, you just say, okay, what would be the proposed solution for t? Well, that would be the a times t plus b. Secondly, what would be the proposed solution for the e to the rt? Well, we've already discussed that. And the proposed solution for the equation that has these two functions multiplied together is just the product of the proposed solutions. One of the things I do want to point out to you is, suppose you have something like t squared plus 7t. Now, we talked about this earlier, but I was concerned that we just talked about it, we didn't actually see anything going on. Notice this is a second degree polynomial. When we include a proposed solution, we have to have all of the powers of t from 2 down to 0. So we have at squared plus bt plus c. Then, since we still have our e to the rt, our proposed solution for that is going to be k e to the rt. A third example of how this would work would be if you have something like t times cosine of something or other times t. So it could be 6t, 8t, whatever. Now you want to be careful here because remember when you're working with cosine or sine, you want to include both a cosine and a sine term in your solution. This does not mean that sine and cosine are going to be multiplied by the same coefficient. So what winds up happening is if you have t, at this point I'm hoping you're getting the hang that the proposed solution would be a times t plus b. That'll work fine for cosine, but we need to acknowledge that it's entirely possible to have different coefficients when it comes to that portion of the proposed solution times sine. Okay, so we wind up with c times t plus d times sine of omega t. Okay, so at this point, we've basically got the idea covered. It's kind of a neat idea. In a lot of cases, it allows for a really quick solution. I'm going to go into a second video where we will also then look at here are some problems, here's how they work.